Hi, everybody. Thank you for coming out to our senior design conference presentation. My name is Haley Gruber, and like Todd said, we are the large RC snowblower team. We have the privilege to work with Fletcher since he is our sponsor, so we get that one-on-one experience.
So, hi, my name is Maverick Beckman.
I'm Breck Maguire.
Okay.
I'm Ben Knockreiner.
And I'm Cherish String. So every winter we have a few givens that always occur in the upper Midwest. Snow, wind, and ice. Snow, as we know, falls up everywhere. It'll be sidewalks, parking lots, and driveways. And as homeowners, you need to be able to move that out of the way to go about your daily life. But when you have to go outside and actually go and move that snow, you have to encounter ice and wind, which can cause slips, trips, and falls, as well as frostbite and other sicknesses, as you're outside in those dangerous winter conditions. So how can we prevent all this physical harm to people and homeowners? What if you made a snowblower that you can control while sitting inside in a warm and safe environment? So that leads into a few senior design projects from a couple years ago, creating two small remote-controlled snowblowers, one using tracks and one using wheels. And taking the successes and failures from both of these and combining them into our own project, we can take a 42-inch front-end snowblower from a John Deere lawn tractor, as well as tracks from a mini Bobcat track loader and drive sprockets, and make our own large remote controlled snowblower.
So with our project motivation established, we can kind of dive into our goals. Our main goal statement is to design and prototype a reliable and intuitive system capable of removing snow via remote control. The system should be cost effective, and then it should also require little intervention aside from the remote controlling itself. Some of our requirements, we need to blow 12 inches of dense snow. It needs to drive by remote control, and it needs to have a camera on board so you can see what you're doing. It needs to have waterproof rated enclosures so that none of our electronic components are damaged by the environment that it'll be used in. It needs to be easy to maintain, so simple parts, simple design, and off-the-shelf parts that are easy to replace if something does break. The front end should attach and detach, and then it should also lift up and down. And then we need multiple mounting points in case we want to add future attachments other than a snowblower to this unit. And then also safety components like an e-stop will have a beacon light as well as other indicators to stop or to prevent injury.
So from our senior design class, we participated in course program, which is immersive and entrepreneurial training program for engineers. So we did interview like 3 people from the program, and first, if our RC snowblower will be sold and used commercially in the future, we should more focus on liability or performance. And second, our customer base will be large homeowners and or small business owners. Third, with the ability to compare to the similar equipment, our snowblower price will be between $14,000 to $15,000. Because visibility is essential for removing snows, especially in the dark. And fifth, our snowblower can minimize insurance claims, so it can help the coverage cost or prevent people get injured. And also, our interviewees are usually comfortable with hydraulic or mechanical systems, so we didn't choose the electrical system. And also, they prefer skid steering, aka like tank drive steering, or more precise turning.
So jumping right into our decision matrix is we had to start from ground up. We had just the snowblowers, we came to chassis. And so now we decided for our drivetrain whether we wanted to go electric, mechanical, or hydraulic. Going into the different criteria, as you can see, we have cost, power efficiency is one of the number ones that we looked into, and then also lifetime. So in our scope of lifetime, that's kind of replacement parts. So the battery, pumps of the different components. Then going into the next slide, you can see that we ranked for lifetime electrical number 1 because we scoped that we saw potentially having to replace a battery before you have to replace a pump or a hose of the hydraulic system. So this ranking out with the other criteria, that hydraulic coming in and winning it all.
The next major decision that we had to make was actually providing power to our front end implement or snowblower. So the main ideas we focused on here were hydraulic, electric, or mechanical, and 3 different mechanical types of gearbox, pulley, or CVT. Going to the criteria, we kind of focused on vehicle integration and compatibility, like how well we can put it with the power drive system that we already picked out, and how well we can actually manufacture it and incorporate it into our unit. And then also how well our operator can actually work with it, whether it be taking it off the front end or just being able to change out parts. And then we also had to look at lead time and if we can actually get these components in time for our build. So overall, the hydraulic PTO1, as you can see, is very close with the gearbox, but we kind of figured that the gearbox is very hard to run a drive shaft to, and hydraulic was a lot easier to use, especially for our operator side.
So then that leads us into our third decision matrix, was our engine. We took into account 8 different engine types, some well-known brands, some not so well-known brands, and some other brands that we just took into consideration that had more aftermarket upgrade parts. So then moving on, boiling it down to our specifications, we only had 3 categories: power, cost, and size. A lot of these engines had the same specs regarding like your alternator size, and making sure that these engines were EFI, which is electronically fuel injected engines, which will just help us work a lot more fuel efficient within colder temperatures. And then moving forward, we actually had a tie between 3 of our engines. And then moving forward, we did decide to go with our Honda IGX 800. This is just because Honda is a very well-known brand, and a lot of parts for maintenance and everything for Hondas is pretty well accessible within any small engine store or hardware store that you can find.
And so up to this point, some other decision matrices that we looked at more so for modeling and also for first semester testing. So one of the things we looked at was frame material, and we decided to go with 1018 steel. We also looked at the front end attachment for the blower itself, and we decided to go with the linear actuator. And we also looked at the track shape, and we decided to go with upside down trapezoid. And then more for the first semester testing, we decided to look at the camera and the controller system, and we decided to go with the radio link controller and the FPV for the camera.
So on the camera side of things, we wanted a simple, low-cost option and something that is pretty easy to integrate into our system. A lot of what we looked at was home security cameras. That's kind of what's been used in the past and for other similar projects. But we figured if we're gonna maybe turn this into a product someday or go that route, using something that doesn't have its own application that we would have to interface is probably going to be easier. So these are very common with remote control projects like RC planes. And these components are very interchangeable. So we should be able to upgrade this if we need to, and we have a lot of variability.
So going into our next slide, we have some decision challenges that we came across. The first one is a drive.
So none of us have ever had experience working with hydraulics, and as we've already shown, that was kind of our main drive system that we've chosen. Starting off with one of our goals of being skid steer controls kind of is that one track has to be able to go forward, one has to be able to go backwards. And to accomplish that, we have to use 2 pumps to drive 2 different motors. So going with a well-known brand name of Hydro Gear, we decided to go with 2 pumps that we can run off like inline, kind of similar to a skid steer that would go off the front of our engine. And then going off of that, we have to decide what motors to use. And as you can kind of see from this power torque curve compared to our speed, where we actually need to operate for our track speed and torque requirements. From our interviews, we found out that people usually blow snow going between 1 and 4 miles an hour. But doing some calculations, figured out that the highest loading you'd have with your tracks was how big of a vehicle we have, and the fact that you have to pull these massive tracks around. You'd have around 960 inch-pounds of torque at maximum loading, but that would occur at your lowest speed of probably around 1 mile an hour or 40 RPM, which means your motor that you're going to use has to be compatible with high torque but low speed operations. Anyone who's looked at hydraulics knows that's a very expensive, very hard motor to spec out. And then going back to our pump, we were able to figure out that we could use both Hydro Gear source products with an HGM motor and a PK pump, but we'd only be able to achieve a maximum speed of around 3.5 miles an hour after looking at hydraulic efficiencies.
And going into our PTO system, we did have a decision matrix on this, and it did resort to hydraulic. But we had three revs of it. We initially started hydraulic to go in with our drive line, and then we talked to one of our other advisors, and he was very concerned about getting the components, other the pump and the motor, in time, for different reasons like that, lead times. So then we talked to our advisor and other advisor and our sponsor, and they go, well, maybe we really want to stay with the hydraulic. So then we had to outsource that direction. And we've been able to find some pumps and the motors that can now work with the hydraulic system, and getting them all in line. So here you can see the engine diagram going into a clutch, going straight into those inline pumps that Cherish talked about, and then going down through a clutch, down to a pulley and controlling the auxiliary pump, going to the motor that is attached directly to the snowblower itself, that has a 1-to-1 ratio, that the motor is able to control 450.
So then for actually attaching and detaching this implement, we want to kind of add future stuff. So we're designing now for the future. We decided to go with a mount style similar to what the Toro Dingo uses. So it's a skid steer style plate that you kind of tilt and lift into, and then it locks down. We've got some preliminary sketches of what our lift might look like. We'll use linear actuators for that, electric ones. It was just a little too difficult and too costly to get hydraulics in there for what we're trying to do, but this should allow us to do everything else specified in our goals.
So then that leads us into our actual block diagram of our system. Within that, we have three main systems: our mechanical, our hydraulic, and our electrical. So starting off with our mechanical, our main three systems is just making sure our chassis is built for the weather conditions that our actual snowblower will be in, along with the integrating the track system that we were given, and then picking out an engine. So then moving on, we have our hydraulics. As we talked about within our previous decision matrices, we have a series of pumps and motors for each of our tracks and our PTO. And that leads us to our last section and most complicated, which will be our electrical. A lot of these hydraulic pumps are going to be run off of servos, making sure that we have full control of the actual speed and forward and reverse of these pumps. With that, it includes our safety features, making sure that we have indicators, beacons, and lights, along with emergency stops and an auger guard.
So here's our electrical diagram. It's a little bit more in depth on this block diagram. So you can see the main things are the camera and the beacon. Those will be running the whole time that the equipment is running. So that's coming straight off the battery. And then we have the e-stop also incorporated with two normally closed systems, so that if it's ejected or if it's set off, everything shuts off, the engine and the battery sourcing everything else. I'm looking at other things is the drive and then the alternators that is sourced into it. And then also looking at the actuators that are controlling the lift and the tilt of the chute. And this is our hydraulic diagram, very simple, going in from the reservoir to the filter and into each individual pump. Then those going into the motors and then going back into the reservoir. And then the yellow line is the shaft power directed into these pumps that are able to make the circuit go.
So this is our radio link remote controller layout. So the reason why we chose this one is it's not too expensive and easy to set up and good for ergonomics. So from the bottom, M1 and 2 are left to right track system controller, and 3 and 4 are top left, 3, 4 are front rear light switch, and 5, 6 are chute, rotation, and tilt. And top right is 7 and 8 are implement, lift, and PTO clutch.
So then that leads us into a modeling aspect of this. So within the first couple of weeks, we knew we had size constraints. Since we do have a 42-inch wide snowblower, that means that our outside width of our tracks can't exceed 42 inches. Otherwise, we're just compacting the snow. With that, one of the actual big engine requirements was the size constraint, as in making sure that it fits in between both sides of our tracks, along with making a justifiable frame. With that, within the modeling, we are also able to model a different track tensioner system that we'll be integrating soon.
So then for our first semester testing, we wanted to do the remote and the camera, but the camera didn't come until yesterday, so we never got to test that. But we did get remote testing done. And then we did some by FEA and some vibration analysis through SolidWorks as well on our frame, just to make sure we're headed in the right direction on design. So for our controller testing, we had right out here, we had Haley and Brecklin stood and they held the controller, and me and Maverick walked out in 100-foot increments. And then we looked at the input time and latency time using stopwatches, and we recorded those. And we didn't see any correlation between latency and distance in that 1,000 feet. So we're pretty confident that for the range specified in our SCR, we will be able to use this controller without any issue. The average latency was 0.053 milliseconds, so not anything we're really concerned about there.
Moving on to some FEA analysis, you can see your frame modeled here that's using the Weldman featured SolidWorks with a 2x2 inch square tubing. Some of the loads that were aesthetically applied to this frame were engine mounting, just some estimated weights for like pumps, electrical box, fuel tank, the front implement mount, and then the track assemblies on either side of the frame. You can see in the top middle picture, that's if you compare the actual stress applied compared to the yield strength, which is around 50 KSI. As you can see, since the whole model is blue and not red at all, it definitely passed the test of the strength study. But then looking at the bottom middle picture, it's more of a proportional scale. You can see the more of the stress accumulated in the rear end of the frame. And then our factor of safety visual is on the top right with a minimum factor 50, 50, 51. That's a bit overkill for this project, but we can also either get rid of some more supportive members or just chalk it up to know that we're gonna have a rugged design that's gonna survive several years and have more mounting added to it. Moving on to the next set of testing for SolidWorks simulations was frequency. We're a little concerned about the natural frequencies emitted from our engine, being that it's 25 horsepower and with the crankshaft running at 3,600 RPM. Doing some quick calculations, I would only produce about 120 hertz. And then based off of the simulation studies, the lowest frequency that our frame would encounter is 176 hertz. So we steer clear of that. We don't have to be concerned about the engine producing any natural frequencies that would cause resonant damage. As you can see in the bottom left, that's what a possible deformation could look like if we did encounter any of these resonant frequencies. And then doing a little bit of random vibration studies on the top right, if the frame was to go through a consistent rugged terrain of like a 2.5 foot or 2.5 inch consistent drops, then we might have to be worried about damage. But at this point, we don't have to worry about that with our main contact point being concrete.
So now going into our Gantt chart, this is just a summary of things that we've worked on this semester. So the big things to highlight are the binder that we have at the end of the year, some social media posts, the video, the Gantt chart. It's a continuous thing. We also have more sections than just assignments and documentations on research. So we have that constant going. We have about almost 150 lines in this Gantt chart. Going to the next one, this is the main things that we have going on next semester, things to look forward to and things we need to get done. Some PRs and some big ones is the full semester demo. We obviously want to do this in the snow, so hopefully we'll get it done before that. So we have plenty of time to test.
And then going into kind of the budget, so as you can see, there's 3 different categories. The first one is our costs that we spent up to this point right now. And then the second one is our estimated cost of the total project, so including all parts given and all of the estimated costs of the parts that we will need. And then the last one is our cost of just the parts needed for our project. And then as there's 2 different like visual representations of the budget distribution. And so like as you can see, there's different categories on like some of the more different types of parts needed. And so like the estimated one that's more considering like if we need like a blower, like anything like that is in for like the drivetrain. And then for our costs, it's one of the most bigger part of the budgets is the hydraulics and the power itself.
Any questions?
Maybe you already covered it and I'm just forgetting, but what snowblower do we plan to use?
We have a John Deere snowblower 42 inch that came off L120, 130, something like that.
I have another question too.
Yeah.
How much is this thing gonna weigh and how do you plan to like drive it on ice and such?
So far the estimated weight is around 800 pounds. And what was the second part of your question?
How do you plan to get it like up a slope driveway if there's ice or something?
So we're kind of hoping that the tracks are able to maintain friction, especially with the weight of the vehicle and at the slow speed that it's going to be going at. If we do have to encounter any like strips we have to go through, we do have that front lift mechanism that'll hopefully be able to kind of bite away the snow if we do have to be able to go through that.
That was also a question that we brought up within our actual track decision matrix. We wanted to make sure that our tracks actually contain the most amounts of surface contact within that. Since this past summer I was working on ACO, working with track tractors, we didn't really need to fully worry about the actual slippage of tracks, just because within tracks you still contain a large area of surface contact. And with that, the amount of weight that we distribute, it should hold up, especially with the track design that we actually chose. Well, actually, the tracks that we were given from Bobcat, if you look into the specification sheet, this is rated 4 out of 5 for actual ice and snow contact. So within that, we don't necessarily see that as an upcoming problem.
I know in the I-Core interviews, we had a lot of people concerned about it. We even asked them what their kind of thoughts were, and they said if anything, you could put studs in. So if we have to, we will look into that.
The motion control, like 2 sticks, 1 for each.
One for each track, yes. So your left one will control your left
Yeah.
from the back.
Are you concerned at all about ease of getting those straight?
I guess I haven't considered
Motors
that quite yet, but
balance.
yeah, we are able to critique the different sensitivity in the remote. Through the different testing that we did, we were able to kind of play around with the different numbers. And then these little triggers on the side, you're able to change the sensitivity as you're kind of moving. So
Sure.
we'll have a setting for it, and then they'll be able to adjust as they want to.
Be able to kill power from the controller, or is it just a physical button on the machine itself?
As of right now, what I've looked into is a physical button, but I know I am still looking into being able to kill it through the remote. It's just an extra step.
What are you using for a chute control mechanism on the blower itself?
So for the rotation of the chute, we have a rotational actuator. So it just spins, and that's going to rotate the whole thing. And then we have about a 6-inch linear actuator that adjusts the tilt.
If I understood your decision matrix correctly, the lift mechanism is going to be a linear actuator. Why did you decide to go with a linear actuator on the lift and got all the hydraulics available?
Yeah, so we decided hydraulics because we would have to have 4 pumps, and Maverick would go into it more, and that would just take more power and the bigger tank for things like that.
So we heavily considered and actually wanted to go with hydraulic cylinders to raise and lower it. One of the main problems, though, when we were talking to Doug Prairie, was that we wanted to kind of offshoot the actual pressure for the PTO to go into those hydraulic cylinders. But the main problem is that since we have to mitigate the amount of pressure, it'd be such a small orifice that the amount of pressure and temperature and kind of just overall wear and tear on the actual orifice wouldn't actually justify it, making it a whole different system. So then making a whole another system to go along with that would just add a lot more complexity and cost.
All right, probably one more question.
Yeah.
I know you guys mentioned adding an e-stop. Have you considered adding any sensor so that if someone gets too close to the front of it, it kills itself automatically?
So we're actually going to put, there's a couple autonomous snowblowers on the market. They're a lot smaller than what we're working with, but they use just kind of about 3/8 or 1/4-inch bar that runs around the front on the lower half of the auger to stop larger things from going in. They're spaced about, big enough that snow can go through them. One of the biggest challenges with snow is it's water, right? So detecting anything through it is going to be difficult. It's something you wouldn't, like if there's things in the snow, you wouldn't see them when you're snow blowing, even if you were out there with your own snowblower. So that's just kind of something where it's kind of unavoidable at the time being.
Speakers?